So someone said it would also be NMR because we also have a hydrogen-carbon difference. So what I want you guys to notice is we have one hydrogen on a double bond, and we have a hydrogen on an oxygen. Whereas here, we have two hydrogens on a single bond. So those are going to be significantly different. So we could use an NMR to tell the difference. So this one was kind of a trick. It's going to be both. Is anyone super confused by my trick? I don't see a no. So we're going to move on. So this second one is, yes, someone said one more time. Yes, so in this case, we have functional group differences because we have an alcohol and a carbonyl. So we are able to definitely use IR. However, in addition, we have one hydrogen here that's attached to a double bond and one that's attached to an oxygen. Whereas on this molecule, two hydrogens are attached to a single bonded carbon. So they're going to have extremely different NMR spectrums. So we could use both of these techniques to tell the difference between these two molecules. So both of them would be effective. Whereas this next example, do you guys think we could use IR to tell the difference between these two? No, because both of them are alcohol groups. So we cross out IR. But can we use NMR? Yes, we can. So if you guys remember from Orgo 1, this is bonded to a carbon attached to two carbons. So this is secondary. And this one is attached to one carbon. So that is primary. So the only difference between these two is how the functional groups are connected. So we have one alcohol and four carbons, one alcohol, four carbons. It's just a difference in how they're stuck together. So that's why it's only NMR and not IR. If we go on to this last one, though, it's kind of a flip-flop of this one. So now they're connected exactly the same, but what's the difference? Yes, so the only difference is in the functional group. So are we going to use IR or NMR? IR, exactly. So something that someone pointed out, which was a really good point, is all right, but in this example, it was a two hydrogen difference, right? And here we have one hydrogen, one is on an oxygen, one is on a nitrogen. Like, why can't we use NMR? That's a good point. However, the reason you can't really use NMR is because everything else is so similar, and both of these would be in the heteroatom region anyway. So this would be such a tiny difference that you wouldn't really be able to tell the difference between these two molecules on NMR alone. So you would have to use IR. Does that sort of kind of make sense so far? Cool. All right. So I will give you about 20 seconds to take a screenshot, write your notes, ask any questions, and then we are going to move on.
For clarification, you said that the one on the right can't be NMR because it's too similar, unlike the one on all the way at the left, right?
Exactly. 100%. And I don't think I mentioned this, but the reason that they would be too similar here and not here is because both of these would be in the heteroatom region. So it's the same region. Whereas here, this would be the double bond region and the heteroatom region, and this would be in the alkyl region. We haven't talked about those regions yet, but I want to plant that seed in your brain to think about. Alrighty. So also, I don't know if you guys noticed, but if you were here earlier this week, these dates and times were messed up, but I did fix them. So if you want to download the new handout with the correct times, that is uploaded for you guys. All right. So let me just make myself a new page, and we're going to talk about something that tends to confuse students a lot, but hopefully it won't by the end of today. So homotopic and heterotopic signals. First of all, before we go into anything, I want you guys to note that homotopic and heterotopic are comparison words. They're not definition words. So if I say that these signals are homotopic to one another, I'm comparing them, right? But I can't just look at a hydrogen by itself and be like, that's definitely homotopic. No, it doesn't work like that. Same thing, like when we say something is more or less de-shielded, you're comparing it to something else. You can't just say something is de-shielded, right? So it's just important that you guys kind of have an idea of how these words can be used. All right. So, homotopic. What do you guys think that means, just from how the word is put together? Same, exactly. So this is essentially going to mean same signal. Versus heterotopic, what do we think? Different signal. Exactly. This is super ugly, but that's fine. If at any point you can't read what I wrote, please let me know. All right, so homotopic, heterotopic, super straightforward, right? But I will draw you an example. Let's say we have a molecule, the simplest thing I can think of. First of all, when we do anything with NMR, the first thing I want you guys to think is what? Does anyone remember? Or if you weren't here, can you take a guess? Symmetry. Yes. Okay. So this has a line of symmetry right down the middle. So just keep that in mind. All right. So first, we're going to draw all of the hydrogens out. And if there's a line of symmetry, that means there's how many signals total here?
Two.
Two, exactly. I'm so proud of you guys. So yes, these hydrogens in blue are all going to be exactly the same. And then these two are going to be their own signal, right? So what homotopic means is that this hydrogen and this hydrogen are part of the same signal. So they're homotopic to one another. Also, we can say that this hydrogen and this hydrogen are part of the same signal. So they are homotopic to one another. I don't have enough room to write it for the yellow hydrogens, but these two, again, part of the same signal, so they are homotopic. They are just the same. For heterotopic, however, I'm going to copy and paste this so I don't waste your time redrawing it. The one good part of online SI is copying and pasting, to be honest. All right. So if I told you guys homotopic is just when they're the same, can someone tell me what I can circle here as an example for heterotopic? What do we think? Yeah, exactly. We can compare a yellow one to a blue one. So this hydrogen and this hydrogen are just completely different from one another. One of them is a CH2, one of them is a CH3. They're just different, right? That's all we can say about it. So you guys are totally correct. Homotopic and heterotopic, though, are umbrella terms, pretty much, right? So we can have more specific terms like enantiotopic and diastereotopic. And I already color-coded them, so I'm not going to ask you which one we think goes under which category. But essentially, enantiotopic is a subtype of homotopic. So the first thing we're going to write about it is that it is still the same signal. So we are only going to see one signal on NMR. They're going to be exactly the same. But can you guys tell me, when we think enantiotopic, what are we looking out for? Mirror images, prochiral, awesome. Okay, so someone said chiral center, and this is where a lot of people tend to get tripped up. For enantiotopic, we're looking only for potential chiral centers or prochiral centers, same thing. And I'm going to just draw right here. We denote chiral centers with a star. So I like to write a star with a P to show us a potential chiral center. This isn't like a chemistry term that's widely used. This is just something I do for you guys. Okay, so I shall give you an example. Let's say we have this thing, right? Is there any symmetry here? And yes, Haley, as soon as I finish Enantiotopic, I will zoom out so you guys can see everything else. Okay, so you guys said there's no symmetry. I kind of disagree a little bit because there's no symmetry across the whole molecule, but there's internal symmetry, right? So you guys have to be careful. I don't know if he really talked about internal symmetry in the first week because I wasn't there the first week, but if we have something like that, there's symmetry down the middle. If we have something like this example, these two methyls are symmetrical, even though the overall molecule is not symmetrical. Does that sort of kind of make sense? We'll do a lot of problems like this, but I just wanted to make sure you guys were familiar with it. All right, cool. So for the purposes of what we're doing now, the symmetry doesn't matter. But I did want to ask, all right, so the next question is, are there any chiral centers present? Oh, we got some yeses and some nos. So someone remind me, what is a chiral center? What is required for something to be chiral? 4 different groups. Awesome. So for something to be chiral, we need 4 different groups. For something to be prochiral or potentially chiral, we need 2 unique groups and 2 hydrogens. And I'll repeat that while I write this. We need 2 unique carbon groups, or just 2 unique groups, and 2 hydrogens. The only carbon on this molecule that has 2 hydrogens was the one I drew here. So does this have 2 unique groups? Yes, indeed. So we can call this a potential chiral center. So why is this position not chiral? Because it has a hydrogen and then 3 other groups. Someone said lacks 2 H's. That's why it's not prochiral. You're correct. But why isn't this chiral? Like, why is that not a chiral center?
It has 2 CH3s.
Exactly, killing it. So these two are the same. It has that symmetry, so it's not chiral. And someone asked something, I missed the question because it like zoomed past, but someone said what makes like 2 unique groups or something. That's a great question. So let's say this is our carbon that we're looking at, right? It has 4 bonds. Let's say that 2 of them are hydrogens. And then here we just have to have 2 completely different things. So we can have a CH3 and an ethyl. We can have a CH3 and an OH. We can have an OH and a chlorine, right? We can have anything as long as they are different than one another. So in this case, we had one CH3 and then we had this big chain. So that's why they're unique. Does that kind of clear it up? Does this only apply to enantiomers? If I don't answer your question in like a minute and a half, ask again, but I hope it's going to kind of make sense in a second. All right. So we have our potential chiral center, right? And Dr. West tends to like give you the whole scientific explanation, whatever, for this, but you know, we're simplifying things here. So instead, all I'm going to show you is we have HA and HB. We're just labeling them. And let's say we do some reaction, and I don't care what the reagents are, I don't care what the reaction is. All I care about is that we're going to replace one of the hydrogens with an OH. So let's say we replace HB with an OH, right? Would it be any different at all if we removed HA instead, or is it going to be the same exact thing? The same. I tricked you. It's not going to be the same. Okay, so someone brought up a good point about wedges and dashes. And so even though they're wedged and dashed, they're exactly the same. But the reason that our final products would be different is because here we would have one R, and as someone pointed out, the other one would be S. I don't know which one is R and which one is S, to be honest, because I didn't do it. I can if you want me to, but it's not, for our purposes, it's not important. All we need to know is that we made a set of what? Well, yes, it's racemic, but we made a set of what kind of isomers? Enantiomers. Yes, because enantiomers are just two molecules that are the same, and they have a difference at one chiral center, excuse me. So these molecules only have one chiral center, and one is R, one is S. So they would be classified as enantiomers. So these two hydrogens are going to be considered enantiotopic since they form enantiomers. So let me zoom in and just write that down. And ta-da! I know that can be a lot. Are there any questions so far about like what this means or anything?
So you can replace the HA or the HB with any group that you want, essentially.
Exactly. And the actual process of replacing it like doesn't matter to us right now. You just have to know that theoretically you could do that. Okay, so does anyone remember anything about enantiomers? Like about their physical properties, chemical properties? It's okay if you don't, but I'm sure someone remembers something. And I'm pretty sure some people are here today that were here yesterday. They would have the same signal. That's true. Someone said they're blanking. That's okay. All right. So basically, enantiomers are like exactly the same. They have all the same physical and chemical property, or I should say, they have all the same chemical properties. So that means these hydrogens are exactly the same. There's no difference between them because these two enantiomers will be exactly the same. They'll have the same boiling point, all that kind of jazz. But fun fact, I know most people here are bio majors or neuroscience majors, and they're probably pre-meds because same. So I like to relate things to bio. Fun fact about bio. Enantiomers are important because all of our receptors and enzymes are all chiral, right? So all of your receptors are actually super stereo selective. So for example, if you have ibuprofen or something, right? One of the enantiomers of ibuprofen are going to give us the beneficial effects of ibuprofen. But the other enantiomer could be super duper toxic. So when you're making drugs, you need to be super careful about which enantiomer works, and then about like separating them, all that kind of stuff. So it's just a fun fact. It tends to kind of help people understand the difference between enantiomers, whatever. Super interesting. Cool. I'm glad I didn't bore you to death. All right. Again, you're not going to be tested on that. It's just a fun fact, so you can throw it out of your brain if you would like. But anywho's, let me move this just so it doesn't get in the way. All right. So any questions about enantiotopic, or can we move on? I'll give it a second, and then if no answer, I will just move on. Okay. I got so excited about the fun fact that it just took all the energy out of me. So I apologize, but that's cool. All right, so diastereotopic, let's remember that they are different signals. So on the NMR, you will actually see multiple signals, like they will not be the same. And we actually have two different cases where we can be diastereotopic. So we're going to look out for chiral centers and double bonds. And I'm going to show you examples of both. So first we'll start with the chiral center. And let's say we have this, right? It's pretty similar to the one we just did, except now instead of a second methyl, we actually have an OH. So unlike the last example, what is different about this molecule? That was a really weird way to say that, but yes, it does have a chiral center. So this right here is a chiral center. And now that we have a chiral center, we have to be thinking about diastereotopic. So if you have a chiral center anywhere on the molecule, every prochiral center is going to have a set of diastereomers. So do we have a prochiral center? Yes, we do. This guy is our prochiral center, or a potential chiral center. So that means these two are a set of diastereomers. But again, what the heck does that mean? I'll draw it out the way I did for the last one. So if we replace HA versus HB, again, we're going to get two different molecules. However, this time I'm not going to do an OH. I'll do like a Cl or something, just because I already did an OH and I don't want to make it symmetrical. You can replace it with anything, so don't like be confused, please. Sorry, sometimes when I write, I can't like talk and write at the same time, because then I just get confused. And I write things incorrectly, and I don't want to do that for you guys. And I'm starting to ramble. All right, anyways. So we replace it with the chlorine, right? Now we have the same thing as the enantiomer set, right? Except we have two chiral centers. So this is no longer a pair of enantiomers, it's a pair of socks. No. Okay, yes, so it's a pair of diastereomers. And someone asked, so the difference between enantiomers and diastereomers is that for diastereomers, they have to have a chiral center already. So the actual diastereomers are a set of compounds that have differences in their chiral centers. Enantiotopic versus diastereotopic is a little bit different because then we're just talking about the hydrogens. So I don't mean to like nitpick you or anything. These are like important keywords that you guys should remember. So now that we got that out of the way. Yes, the difference is basically in enantiotopic, you cannot have a chiral center present. You just have a potential chiral center. If you have a chiral center present, then it's diastereotopic. Does that answer your question? Yes, okay, sweet. So these two hydrogens will give you two completely different signals. So let's go ahead and count signals for this one. First, we're going to start here. And are these three hydrogens going to have any symmetry anywhere else in the molecule? No, so it's going to be its own thing. And then we know we have this signal, and then we have a signal here, and we have this signal here, and last but not least, we have this signal here. So how many total hydrogen signals will we have? And yes, HA and HB are going to count as two separate signals. So altogether, can someone count for me?
Rose, I have a question.
Yes.
I think that's where I'm getting sometimes confused of determining when, let's say, HA and HB are different. Because I remember I had Chris last semester and he was saying how it's the same only if it's different only if there's like another existing dash or wedge in the molecule. So I think that's where I'm having a little confusion determining if like the same hydrogen coming from two hydrogens coming from the same carbon are the same or different.
Yes. Okay, that's a great point. So in Orgo 1, Chris explains it a little bit differently because you guys don't need to know it. Like you guys have to know it on a more basic level. So in this class, he will try to trick you by putting wedges and dashes where they don't belong, right? So sometimes he'll just give you this. And so it makes you think, oh, wedge and dash, chiral, that means these are different. But what you more so have to pay attention to is chiral centers. So we see in a molecule, this one does not have a chiral center, so they will be the same. In this one, sorry, let me zoom out a little bit. In this one, we did have a chiral center, so that's when it then counts as different. Someone said that it cut off for them, so can you guys like not hear me now? Or is it the screen that got cut off, or? You're good? Okay, cool, sweet. Okay, no worries. I just wanted to make sure I didn't like spend the next 20 minutes talking to myself. So yes, the difference would just be whether or not there's a chiral center. So if there is a chiral center anywhere in the molecule, all of these hydrogens will be different. All the CH2s will be different. However, if there's no chiral center, they're going to be the same. Is that cleared up like just a tad, at least? Yes. Okay, cool. So we are going to go and do some examples super quick, but all right, so this one, some people said 5, some people said 6. This is a trick because people always do this. I don't know why you guys hate this guy and this guy, but half of my students will forget this one, half of my students will forget this one. So altogether we have 1 signal, 2, 3, 4, 5, 6. So altogether we have 6 hydrogen signals. For funsies, someone tell me how many carbon signals there are. 4, exactly. 1, 2, 3, 4. Carbon tends to be much more straightforward. All right, so someone said, is it screenshot time? This was like a little bit ago, but we have one more thing before it's screenshot time. I don't know why it's being annoying. There we go. Sorry for all movement. So the second case is going to be double bonds. So let's super quickly go through all the double bond possibilities. Okay. So someone says, so heterotopic is coming off of different carbons, but diastereotopic is coming off the same carbon. So really quick, I want to mention anything that's diastereotopic is also heterotopic, right? Because this is a subcategory of this. But diastereotopic is super, super, super specific. So yes, if two hydrogens are on the same carbon and they're different, they're diastereotopic. Anything that's different, though, is considered heterotopic. Same here, right? So homotopic is everything that's the same, and enantiotopic is a specific example. So everything that's enantiotopic is homotopic, but not everything that's homotopic is also enantiotopic. Those are a lot of words. It sounds like gibberish, but I hope that makes sense. All right, so let's do the double bond super quickly, just because I don't want to leave you guys without this finished. All right, so when we see double bonds, we do the Rosemary method. Rosemary method is cut it in half. And when you cut it in half, you have to actually cut the double bond. And you're left with carbon 1 and carbon 2. The naming it 1 and 2, or numbering it 1 and 2, excuse me, is just arbitrary. It's not based on Newton, like IUPAC, whatever. Just one of them is 1, one of them is 2, so you can differentiate, right? And so what we want to consider next is that both of our hydrogens have to be on the same carbon. So in this case, HA and HB are both on carbon 2. Step 1 checks out. Step 2 is make sure the other carbon has 2 unique groups. So we don't want symmetry. In this case, does that check out? Sorry, I can't sit like a human. Yes, it does check out. So we have 2 unique groups. Sweet. So the reason that's important is because if we substitute the double bond, depending on which side we substitute, we're going to get what? Not enantiomers, not RS. Yes, diastereomers, but there's a better word. Yes, we get EZ or cis trans. So in this case, Cl is going towards the smaller side. So is it going to be E or Z? Or we can say cis or trans. Trans, exactly, because the priority group is this, priority group is this. And in this case, they will be cis. Can we flip between these two? No, because the double bond is rigid. You can't rotate around a double bond. So in this case, what is the relationship between HA and HB? What do y'all think? They're cis and trans, yes, but even, hold on. Sorry, it's really hard to spell diastereotopic, so I can't talk and spell at the same time. Yeah, so they will make cis and trans products, but the 2 hydrogens themselves are best categorized as being diastereotopic. And so someone had asked me what step 2 was, and we're going to do it again now in the second one. So the first thing we do is cut it in half, right? Next, what do we do? We number them 1 and 2, exactly. Also, I know it's 12:22, but I'm just going to keep going and finish since this will be recorded and we had to finish, or we had to start a couple minutes late. If you have to leave, please do the attendance and then go. All right. So after we pick 1 and 2, what's step 1? Make sure the hydrogens are on the same carbon, and that checks out. What's step 2? No symmetry on the other carbon. Exactly. Does that one check out though? No, exactly. So now these two groups are both methyls. So we have symmetry. So they're no longer diastereotopic. Does anyone want to take a guess at what their relationship would be now? Someone said enantiotopic. That's a good guess. However, does it have a prochiral center? No, exactly. So no prochiral center means it can't be enantiotopic. And so some people said it will be homotopic. They will just be exactly the same. So for this next one, we're going to cut it in half. Carbon 1, carbon 2, 2 hydrogens on this side, 2 different groups on this side. Cool, right? Everything seems to be good. So will this hydrogen and this hydrogen be diastereotopic? Yes, so these two will be diastereotopic. Will this one and this one be diastereotopic? No, absolutely, because like we said, they have to be on the same carbon. So it's okay if we have a hydrogen over here. Yeah, someone said they're confused because it has 3 hydrogens. Exactly. People tend to get tripped up. So as long as there's 2 hydrogens on one carbon, the other carbon can have whatever groups it wants, right? So it's allowed to have 1 hydrogen, as long as it doesn't have 2 hydrogens, because they can't be symmetrical, right? So technically, this one does follow the rules. So the 2 hydrogens on carbon 1, the 2 hydrogens on carbon 2, or I'm sorry, the 2 different groups on carbon 2, but, hold on. So someone said, I thought I had to have 3 different groups. So it doesn't have to have 3 different groups. It just has to have 2 different groups here and 2 hydrogens. So that's why I always say to cut it in half, because it can kind of be confusing if the groups are like oriented differently. So again, as long as the 2 hydrogens are on carbon, this side is allowed to have a hydrogen as long as it has another unique group. Is that starting to make a little bit of sense? If not, here, let's draw this real quick. Bam. So basically, we can see that these 2 hydrogens will give us these 2 products, right? And so it's okay that we still have a hydrogen here because we're still going to get cis and trans. And so someone basically summarized, so basically it's allowed to have a hydrogen and another group as long as it has 2 hydrogens on one side. Yes, absolutely. So if instead we had something like this, the next example, so we cut it in half, right? And we have carbon 1 and carbon 2. It has 2 hydrogens in this example, but are they on the same carbon? No. And it has 2 unique groups, but are those on the same carbon? No. So both step 1 and step 2 don't work out, right? So these cannot be diastereotopic. What's their relationship going to be instead? Any guesses? Heterotopic, exactly. And that is because they're just completely different from one another. They're on completely different carbons. So something I did want to write in case you guys look back at this later and you're confused. So let's say HA, HB, and HC. So in this example, HA and HB, diastereo. HA and HC, hetero. HB and HC, hetero. Just so you guys like have it in your notes. Also, I'm going to flip this around on my end so it fits on the screen. Is this better or worse for you guys?
I don't know. It looks a little worse.
Okay, here you go. So I'll do it once all the way zoomed out, and then I'll zoom in to half and half, if that makes sense. Bam. Okay, so now I'm going to zoom in to this part. And then this part. All right. And just in case, I'll zoom out all the way one more time. And I will send you guys the attendance link one more time. Pretty please fill that out. And then I know we went over time. Thank you to whoever stayed. I apologize for that. The technology was being super weird. If anyone has any questions, I will stay for a couple more minutes to answer them for you. If not, I hope you have a wonderful day, and I will see you all next week. You're very welcome. Thank you for all the participation. You guys did amazing. I'm so proud. I wish you guys could see the smile. I'm smiling at you. I'll stop.